Okay, now in terms of types, here it is. We have electrical sources, and we say that it's classified as voltage source and current sources. And further, we can classify this voltage source as independent or dependent. Current source is still the same. We classify it as independent or dependent. And you notice the symbols right here. For independent source, voltage source, we just have a circular or a circular shape. The same is true for the current sources. We have the circular shape and an arrow. That's for current. Plus minus for voltage. But when we say dependent voltage source, that's just a diamond. And plus minus symbol for current sources, we also have a diamond and an arrow sources. Right, so when I say independent, just simply a source of voltage that is entirely independent of the circuit. So meaning it produces its power independently from the circuit. When we say dependent, then of course the power produced is somewhere affected or depends on somewhere in the circuits. Okay, so for dependent, we further classify it as VCVS, or voltage controlled voltage source, or current controlled voltage source. And for this one, we have voltage controlled current source and current controlled current sources. Right, so just some terms that may be necessary in our computations. Right, if it happens that we encounter this in some of the circuits later on, right? But anyway, now let's move on to the sign convention. Right, so as for the sign convention, we have this term passive sign convention. So the sign convention is based on the passive elements. So for for a passive elements, let's say we have these elements right here. Recall that passive elements, they're the ones consuming the energy. Let's say we just use a box symbol right here, rectangular symbols. So we have a voltage across this element, right? So we can label this plus and minus. So that's going to be the polarity of the voltage, and there's going to be some flow of current. So when we say under the passive sign convention, that means that the positive I, the positive current, enters the positive voltage, right? So positive I enters the positive voltage, whereas in active elements, the positive I enters the negative voltage. Right, so in terms of voltage, if this enters right here, right, so from positive to negative, then that's going to be a voltage drop. But for this one, from negative to positive, that means it's a voltage rise. Right, and for the currents, as I've said, that positive current enters positive voltage terminal. For active elements, positive current enters negative voltage terminals. Now in terms of power, the positive power right here, positive power for passive elements. So that simply means that if it consumes power, then the sign convention is it has a positive sign. So active elements, meaning it's negative, it just simply means that it produces power. Okay, so in say positive sign convention, then this applies right here. But for active elements, this will be the sign convention. Okay, so in terms of analysis later on, voltage polarity or current directions are just simply assumed arbitrarily. I mean, initially we just assume it, but later on in the computation, let's say if we found out that it's going to be negative, then this simply means that the current direction would be opposite, right? So let's say if right here we have this positive I and this plus minus, we let's say we just assume arbitrarily that this will be plus and minus, but later on, if in the computation, let's say we it happened that the I direction is negative, then that simply means it's the other way around. That simply means that it should be right here, going in this direction, right? So it's not a passive element, but rather it's an active element. So just like what we did in mechanics, like first just assume that all the directions to the right are positive, right? So summation forces x equal to 0, and later after the computation, once we found that it's negative, then it just simply means that it's in the opposite direction. Now let's move on to electric circuits. Now let's say electric circuit, it consists of various types of elements connected in closed paths by a conductor. Right here we have a simple circuit. We have this voltage source, a switch, and a load, and they're connected together by these conductors. Right, so if the switch is on, then there's going to be then this load will light up. Right, so some couple of terminologies that we'll encounter is sometimes you hear the term closed circuits, open circuits, or short circuit. And what that means is that if it's a closed circuit, then there is an uninterrupted flow of current. So because it's closed, then the current can actually pass through that terminals, right? Because it's closed. If it is open, then it cannot pass through, and therefore, if it's open, then there's this. Let's say if this is a lamp, then it's not gonna light up. And when we say short circuit, it's a term when there is an unintended path circuit. So let's say there shouldn't be a path right here, but because it's shorted, maybe there is water that spilled, and somehow there's gonna be connection between this. So that's gonna be what we call short circuit. Okay, and for the analogy, there's actually a resemblance between the electric circuits, the fluid systems, and thermal systems. Because right here in electric circuits, we say that there must be some voltage, so that the charge can move from one point to another, right? So that the charge, or so that there's going to be a flow of current right here. So if it will have a continuous flow of current if, of course, it's going to be in a closed path, right? So there's going to be a driving force, and that driving force is the potential difference from this battery. Now for thermal systems, in order for the heat to flow, so in order for the heat to flow from higher temperature to lower temperature, there must be some driving force. And that driving source, although it says here heat source, is actually the temperature difference. Right, so because it's hot here and it's cold there, so hot and cold, so because there is a temperature difference, then there's going to be a flow of heat. Now in fluid systems, driving force is the pressure difference. Let's say we have the piping systems, so we have this pump right here, and also the flow of water is actually from higher pressure to lower pressure. So just like here, higher temperature to lower temperature. But of course, this is just in closed pipe systems. In fluid mechanics, we've also learned about the open channels. So it's a different types of systems. So for this one, it's the pressure difference that drives the flow, right? And the pump is a device that produces, or that increases the pressure, so that the water can flow from this point to that point, right? Okay, and because of the driving force, the ones that the flowing right here in electric system is the current, and for thermal systems that's heat, and for fluids that's the liquid or the fluid that flows, right? So that's the flow rate. And as that fluid flows, or as that heat flows, or as the charge flows there, it actually experiences resistance, and we call this electrical resistance of the wire, or if we have resistors. And for thermal, there's going to be resistance related to geometry and the material properties, just like in your heat transfer course. Let's say there is a wall right here, a solid wall, so heat transfer, let's say higher temperature right here, high T and low T on this side. So as it travels, or as heat travels right here, there's gonna be a resistance, so resistance coming from the wall material. So that's, let's say, conductivity. Okay, and what else? For fluid systems, we have resistance from the wall of the pipes, so pipe frictions, and also the viscosity of the fluid itself, and also the flow conditions. So there's a lot, but there is a resemblance, as you can see here. And for the governing equations, we have right here. So those are the analogy for the electric circuits. Okay, so now let's talk about the nodes, branch, loops, and mesh. Okay, because the study of electric circuits, we also need to be familiar with these terminologies. Right, so when I say node, it is a point at which two or more components are connected together. Let's say here's our circuit right here. Now, when I say a point at which two or more components or elements are connected to each other. So right here, let's say here's our first component, right? And here's our second component. So this point right here, that's gonna be a node. Okay, so what else? Let's say here's our first component and here's our second component. So this will be a node as well. And what else? Now, in terms of diagram, this will be a node as well, right? But this is a component. This is also another component, and this will be a node. However, it's just simply, if we shrink this down to 0, this is an entire node, right? So we keep this in mind. If we shrink this down to 0, this is actually an entire node. Okay, so because we can actually right here, it's still the same if we include this. So basically, our nodes, we have 3 nodes right here. Let's say here's our node A, our node B, and our node C. This is our A, B, and C. So if we redraw this, here's our voltage source. So it's connected, right? So it's connected to this resistor, and this resistor is connected to this node B, and the node B, it all branches together to this resistor, another resistor, and this current source, right? So we have 3 nodes. Okay, when I say branch, it's any element connected between 2 nodes, so therefore this will be 1 branch, right? So 1, 2, 3, 4, and 5. Right, so we have 5 branches. So 1, 2, 3, 4, and 5. Okay, next one is loop. So when I say loop, it's any closed path in an electric circuit. And when I say closed path, that means that let's say I start from this node, right? So if I start from this node, then if I trace a path, a closed path, then I go back to the initial node. So that's going to be one loop. Okay, another loop is, let's say I start right here, right? Or let me redraw it here. So this one, this will be the path, right? So another one, if I start from this point right here, and then I trace a closed path, and I go back to where I start. So maybe right here, right? So that's another loop. Okay, so another one is if I start from this point, then I trace a closed path and I go back to this original point, then that's another loop. So we have 1, 2, and 3, but there's still one more, because there's still many other loops, because we can also trace, let's say here's our current source, our voltage source, and here's our resistors. Okay, another one is this. So let's say I start from this node, right? So a closed path, then this is another closed path, so that's another one, right? So this will be our fourth loop, and another loop that we can create is this. So start from here and I go back to this, so that's going to be another loop number 5. And finally, the outermost path, maybe I'll use this blue. So I start from this node and I go back to this, so that's the outermost closed path that I can travel, and that's still another loop. So we have 6 loops. But as you can see, a loop may contain a loop, like contain more loops. Like for example, this 6th loop, it contains many other loops inside, or the loop number 4 that we have contains two more loops inside. And when we say mesh, that's actually a special type of loop that does not have a closed path in its interior. So basically, loop 1, 2, and 3, those are the meshes that we have. Okay, so in the study of these terminologies, it gives birth to this terms, series and parallel connections, right? So when we say series, when 2 or more elements share a single node. So let's say here's our circuit right here, and we have these nodes right here, and we have these nodes right here. But in terms of let's say right here, this element right here, they share the same nodes, but this end is not shared to that end, right? So only a single node is shared, then that's what we call a series circuits, right? So this resistor is in series to this resistor, and is series to this voltage source, right? So we can also redraw it. So just take note that when we redraw, we're not actually changing the connections, right? So this is one way. So this is still in series, right? So series connections, right? So the connection point is let's say between these two resistors is this point right here. Now for parallel connections, when 2 or more elements are connected to the same 2 nodes. So 2 nodes, they're common, they're connected together. Like for example, this resistor and this resistor, they're connected in this with this node and these nodes. So end to end, they have the nodes connected together. Right, so if we redraw it, something like this, and it's also that this node is actually connected, is in a parallel to this voltage source, right? So in characteristics, so for series, if we have this charge right here, let's say here's our negative, so positive current enters the positive oh sorry, since this is active circuit, so it's gonna be like this one. So when the current flows, then the this current will flow through this resistor, and then the same current will flow through this resistor, and then it will go back. Right, so that's why this series connection has the same I, same current. In terms of parallel connections, the voltage potential of this potential, it has the same potential across this branch right here, and it has the same potential across this branch. So same voltage. Alright, so those are the terms that we'll discuss for now. We'll go into the detail of this once we, I think in the next week topic on resistors, then we'll talk about this in detail. Okay, so next one we'll discuss this. Okay, sample problem 1. Okay, so right here it just says determine the number of nodes, branches, and loops for this type of circuits. We just have these generic symbols for the elements. We have A, B, C, D, and E. So doesn't matter whether it's active or passive elements. Right, so to do that, so for the solution, okay, so number 1 is the number of nodes. The number of nodes is, so we'll copy this, Control C, and what else? Control V. Right, so we'll copy this and we'll label. So nodes is connection between two elements. So this is one element. So we have this. We'll use red color, right? And this is another one, right? So connection point, and also we can draw it up to this point, or we can draw, if you'd like up to here, provided that you know that this will be the branch, right? Right, so these are the nodes for the circuits. Okay, next one is, okay, the number of branch. So number 2. Okay, the number, or I forgot to write. So there are 3 nodes. Right, the next one is the number of branches is since this is our node, then the branch will be, this will be branch, this will be branch 1, right? Branch 2, branch 3, branch 4, and branch number 5. So we have 5 branches. Okay, next is loops. Okay, so the number of loops is, so we need to copy this. Alright, so we'll trace the number of loops we have. We'll start from this point. Alright, so we have 1, we have 2, and we have 3. Okay, and also another closed path will be this 4, and maybe this. We'll try this 5, and the other one is 6. So we have 6 loops. Okay, so for our first sample problem, we have this circuit and it says determine the number of nodes, branches, and loops. So we have this circuit, the elements, they have this generic symbol, A, B, C, D, E, rectangular shape, and doesn't matter whether it's active or passive. It's so first is, for the solution, then the number of nodes is, so we have to redraw this. Right, so here's our node, right? So we know that this is a node, this is a connection, and this is also a connection. So we have 1, 2, and 3. The number of node is, or we'll just write, we have 3 nodes. Okay, next is the number of branches. Right, so since this is our node, then our branch would be this, so that's gonna be 1, right? So this will be 2, this will be 3, 4, and 5. So we have 5 branches. What else? Number 6 is, sorry, not 6, this is number 3. So the number of loops. So for the number of loops, let's say we'll start from this point right here. And so if we trace a closed path, this is one loop. If we start from this point, we have another closed path, that's path number 2, and right here we have path number 3. Okay, so another one is, if we start from this point, this will be our another closed path, or if I start from this point, this will be my other closed path. So that's my loop number 5, and also we can have this path right here, so that's gonna be path number 6. So this will be 6 loops. Okay, so next one is determine the number of nodes, branches, and loops. So let's try not to draw this in detail. So for the number of nodes, we have 1, 2, or maybe we'll draw this in detail. So solution, right? So the number of loops, the number of nodes, we have this C element. Okay, so for the number of nodes, we have this. So this will be a connection point, this will be another connection point, and this will be another connection point, right? So 1, 2, and 3, and therefore we have 3 nodes. Next one is the number of branch. Maybe we, for the number of branch, so we have, let's say, branch number 1, 2, those 3, 4, and 5. So we have 5 branches. In terms of loops, so we have 1, right? We have 2, and we have 3, and we have this 1, 4, and we can have this 1, 5, and we can have this entire block. So it's the same as the previous ones that we have discussed. Right, so we have 6 loops.